Hey guys, Mr. Betts here. I want to talk more about Taylor polynomials. I talked in the last video about how we got the idea of Taylor polynomials, and now I want to look more specifically at formulas and stuff that we're going to use with Taylor polynomials. So I went through a process of how we got a Taylor polynomial that was a second degree by taking a general form of a parabola and taking derivatives twice and setting it equal to the second derivative of the function. And that gave us the coefficient for the second degree term. Well, if we go through that process for any degree term, what we're going to end up with is a coefficient for any degree term that is going to be in this form. So it's going to be the nth derivative of the function evaluated at the center. So in the example I did, I centered it at 0, but we could use any point of tangency we want, and then divided by n factorial. And that n factorial comes from the fact that when we take derivatives of, say, something like x to the 6th, then we're going to get 6x to the 5th. And then we take the derivative of that and we get 6 times 5x to the 4th. And then we take the derivative of that and we get 6 times 5 times 4 x to the third. And you can see that as we continue that process, eventually by the time we take 6 derivatives, we're going to end up with 6 factorial. So that factorial comes from the fact that we're taking derivatives of higher degree polynomial terms. And so this gives us just a general way of finding a coefficient for any term in a Taylor polynomial. The general form of a Taylor polynomial itself is going to look like this. And this looks kind of complicated. I have it written first here as a sum, but I think it's a little bit easier to see what's going on if we expand that out. So when we plug in k equals 0, a couple of interesting things happen. When k is 0, we have 0 factorial in the bottom, and we have the 0th derivative on top. So a couple of notes, 0 factorial is equal to 1, kind of a weird thing. You can't do 0 times whatever and decrease all the way to 1. So this is a definition that has to do with combinatorics and counting things. You don't need to know how it got there, but you do need to know 0 factorial is 1. The other thing to keep in mind is that the 0th derivative is just another way of saying the value of the function. So the 0th derivative is the function, the first derivative is the first derivative, and so on. So when we plug in 0 for k into this expression right here, it's just going to be f of a. Okay, that simplifies quite a bit when k is 0. Then we have the first derivative times x minus a to the first power, the second derivative times x minus a to the second power, and you'll notice that every term besides the first one has this x minus a in it. And what that does is it takes a function and it shifts it to the right a units. So if a is, say, positive 1, what it does is it takes a function that would be centered at 0, shifts it right 1, and now it's centered at 1. So this formula right here includes that general coefficient formula, but it also includes the x to the k or x minus a to the k. This is a formula that we're going to use and just plug stuff in, and as you get more comfortable with it, you'll probably get to the point where you don't really need to know the formula, you just need to know how to do things with Taylor polynomials. Another definition, a Maclaurin polynomial is a Taylor polynomial, but centered at x equals 0. So in other words, another way of saying Taylor polynomial centered at x equals 0 is just to say a Maclaurin polynomial. Maclaurin polynomials are generally easier to work with because we're plugging zeros in. So if you go back to this formula here, if a is 0, then we're evaluating derivatives at 0, and this just becomes x to the k instead of x minus a to the k. So Maclaurin polynomials are usually easier to work with, and we'll do those more often than not. But sometimes we do want to center it at other points, and you'll see in some of the examples why we might want to do that. So a few notes before we wrap this up here. The first one is, in many cases, as the degree increases, the nth degree polynomial will approach the original function over some interval. Okay, so here's what that means. In this example here, I have the graph of sine on here in the dashed red. And then I also have the first degree Taylor polynomial, which is also just a linear approximation. And you'll notice that in some neighborhood here around x equals 0, they're pretty close. But then as we get farther away, they diverge pretty quickly. They go away from each other pretty quickly. If we look at the third degree Taylor polynomial for sine, this is a much better approximation over a much wider interval. And then the approximation goes off and becomes not very good after a little while. If we look at the fifth degree Taylor polynomial, now it looks like we're good. We have a pretty good approximation all the way from negative pi over 2 to pi over 2. So the difference between the sine function and the approximation using a Taylor polynomial is getting smaller over a bigger interval. I'm going to jump way out now to the 17th degree Taylor polynomial. So if we were to write out a 17th degree Taylor polynomial approximating sine, this is a really good approximation from well beyond negative 2 pi to positive 2 pi. Nope, I'm sorry. That's negative pi over 3. Negative 2 pi here to positive 2 pi. It's a pretty good approximation in that interval. And then it does veer off and go away from the sine function pretty quickly beyond that. But as we add more and more terms, the range that this is a good approximation for is getting bigger and bigger. And notice that in that range, they're almost identically the same function. So these Taylor polynomials are a really good approximation for other functions over some interval. It turns out for the sine function that we can make it accurate as wide of an interval as we want if we use enough terms. So when we say over some interval, some functions, that interval is restricted to some finite interval. With the sine function, that interval is actually infinite. We can make this really approximate over a really wide interval, as wide of an interval as we want, by using enough terms. Now, we would have to use lots and lots of terms to make it really wide, but we could do it. Second note, Taylor polynomials for a function centered at x equals a can be used to approximate the function of f near a. That comes from the fact that when we graph them, you can see that the graphs of the two are almost identical over some interval. And so especially as we're close to the center of that interval, the Taylor polynomial is a good approximation. Now, I want to point out here that the reason we want to use polynomials to approximate things like the sine function is that polynomials are a lot easier to work with. All right, if we want to know what is the sine of, say, 1, we have to use a calculator or computer to do that for us with any kind of accuracy. Well, if we have a Taylor polynomial that can approximate the sine of 1 for us, we can do that pretty quickly using a polynomial and using rational fractions that we can add and subtract and is relatively easy and straightforward. So we can use these Taylor polynomials to approximate. I did a couple examples here. So I approximated the value of the sine of 1 using a 5th degree Taylor polynomial. And you'll notice that that approximation is good all the way out to the 10,000ths place. It's off by about 2 10,000ths. But then if I expand this and use a higher degree Taylor polynomial, this is the, it says 5, but this is supposed to be a 13 here. This is the 13th degree Taylor polynomial for sine. Plugging 1 into this polynomial right here gives us this, and plugging 1 into sine gives us this. And you can see that this is accurate all the way out to the 12th decimal place. So this polynomial, which is a pretty complicated polynomial, but a lot easier to work with than the sine function, is really, really, really accurate. So even if we're doing things that need to have super high precision, we can use Taylor polynomials, and we wouldn't have to go nearly as far as this and still get the kind of precision that we might need for approximating with Taylor polynomials.